Okay, you guys, here we go. Today we're going to talk about an even more abstract concept than the electric field, which we talked about last time, okay? What we need to do is define electric potential. Hey, look, there's that word define. This is from the IB syllabus. They expect you to understand what electric potential is and electric potential energy. They are closely related. Notice that there's one word different between them, which makes them slightly different but related. You should be able to state and apply the expression for electric potential due to a point charge. You should be able to state and apply the formula relating electric field strength to electric potential gradient. We'll talk about that. You should be able to determine the potential due to one or more point charges. We'll talk about that. Describe and sketch the pattern of equipotential surfaces due to one and two point charges. We will look at that. And finally, state the relation between equipotential surfaces and electric field lines. Today's lecture is dedicated to, who's not here today? Taylor, Isabel, and Steve. We can't forget Steve. He's gone too.
Hayden's gone as well.
Okay. And Hayden. Shoot, sorry, Hayden. We miss you guys. Come on back. All right.
You know he's going to go off this.
He's going to be all mad. Come on, Hayden. Come on. Okay. Work and potential energy. Let's do a little review first. Who remembers what potential energy is? We talked about it last semester.
It's the energy something has at rest.
Excellent. It's the potential to do work. It's energy that's stored within an object by virtue of where it's located, and it gives an object the potential or the ability to do work. It's energy that something has by virtue of its location. And previously we talked about it. We always have to measure it relative to some point. And remember, with gravitational potential energy, we said, oh, we can just call it mgh. That's relative to the ground or to what it's going to fall to. And that's nice for small distances. But for larger distances, we needed a more universal measuring point, and we said that was infinity. And we got into those weird equations where you could find the potential energy of an object relative to infinity. That was all gravitational potential, and that was great because we were dealing with gravitational fields. Well, guess what? When we have an electric field, the same thing holds true. Something can have potential energy because of an electric field. We call that electric potential energy. Think about two charges that are attracted to one another. Well, there's potential there. There's potential energy there, right? Potential to do work. If I release one, it's going to fly and collide with the other one, and all that energy stuff's going to happen, just like with the roller coaster falling through a gravitational field. So we're going to talk about potential and potential energy in terms of electric potential today. Work, again, is another concept we talked about last time. Force times displacement, and the more general equation was Fs cos theta. But work done on an object either changes its potential energy or its kinetic energy. When you do work, remember, work and energy are interchangeable concepts. Doing work on an object either gives it potential energy or kinetic energy. In an electric field, the same holds true. So like I was just talking about, you guys, all of these concepts that we've been dealing with gravitationally, we're going to work with today electrically, okay? It takes work to move a charged object through an electric field. Remember, an electric field exerts a force on a charged object, so therefore there will be work. It'll take work to move it through that field. Therefore, the potential energy, the electric potential energy of the object will have changed. Let me show you a picture of what I'm talking about here. Let me show you kind of a picture of what I'm talking about. So this is the rock and cliff analogy to electricity. All right? So you know that if you lift a rock up, you give it potential energy equal to the weight of the object times the height, mgh. Remember we talked about that? That's just force times distance. Work done, potential energy gained. If the rock were larger, even though I lifted it the same height, it would have more potential energy because it has more mass, right? Well, in electricity, the same analogy can be thought of. Here is an electrical field. What direction does the electrical field go here? Okay. From positive to negative. And what's it look like? Nice and uniform. Here, it'll be a little circle there, but we don't worry about the edge effect. Nice, uniform electrical field, E. Okay? Notice that in order, let's call these positive charges, positive Q and positive 2Q. It took some work to move it this way. There had to be a force applied to move it that way because the field is pushing it the other way, right? Just like lifting a rock. So now this thing has some potential energy, electric potential energy.
Because they're positively charged to their test charge.
Well, because it doesn't have a negative, I'm going to say they're positive. Okay. If I was to release this object, let it go, what would it do? It would move this way. Talk to me about how it would move.
Fast.
Would it be uniform velocity? No. It would speed up. Would it be uniform acceleration? Yes, just like the rock falling, because it's in a nice constant field, it would have a constant force, constant acceleration. Excellent. What? Notice that this object has twice as much charge. Does it therefore have twice as much potential energy? Of course, just like a rock that has twice as much mass at the same location would have twice as much potential energy. Okay? Make sense so far? Here's the concept we're going to try to grasp today. Let's remove the charges and remove the rocks and talk about the location. That location has a property that's common to all objects, as does this location, and it's called potential. It's not potential energy, it's potential. And it basically, when we talk about potential, we're talking about the location. We're talking about how much energy, potential energy, something would have if it were there, okay? And the cool thing about potential is it is constant. Potential energy is different. Notice this one has twice as much energy as this one, but they both are at a location that has the same potential, all right? That's kind of the concept we need to grasp today. There's another picture. Look at that. Awesome, okay? Uniform electric field, high potential energy for right there, low potential energy for right there. Please recognize that with charge, unlike mass, we have positive and negative, right? We only have one kind of mass, we have two kinds of charge. So if I was to place an electron right here, would it have high or low potential energy? Low potential energy, okay, just because it's oppositely charged. But an electron over here would have high potential energy, okay? So the weird thing about electricity that's different than gravity is it can kind of go both ways. Gravity goes one way, okay? Okay, here comes the math, here comes the terminology, all right? So the idea of potential is how much energy is per unit charge is stored in a given location. But what we really want to know is what's called potential difference. And generally, when we're talking about potential difference, we will just call it voltage, okay? Technically, if something has a certain potential right here, that's fine. But really what I want to know is the difference from here to here. It's kind of like knowing how high the cliff is, okay? The potential at a given location can be helpful, but really we usually talk about the difference in potential from one location to another. And when we talk about potential and potential difference, it is the potential energy that something has divided by how charged it is at that location, okay? That is our definition of potential, the potential energy per unit charge at a given location. Again, it's a property of the location. So in our analogy before with the cliffs and stuff, you can think of potential as being the height of the cliff. Okay? It's kind of like the height of the cliff. If this tells me how much energy something will have, and let's go back to our cliff analogy with rocks. If I put a small mass here, it will tell me, I can figure out how much energy it has. I know that a bigger mass will have more energy there. And potential is really just telling me the height of the cliff. So by definition, potential is how much potential energy you have per unit charge, or in this case, it would be per unit mass. More potential means a taller cliff, okay? Or more voltage means a taller cliff. Voltage is potential, yes. We will often call it voltage, but it's basically voltage is the difference in potential between two locations. Okay.
Yeah, exactly.
All right, so here's kind of a mathematical definition then. Oftentimes when we write V for voltage, what we really mean is delta V for potential difference, for change in voltage. And the potential difference, or the voltage, equals the work done in moving an object divided by how charged that object is. The work done in moving it from point A to point B divided by its charge is equal to the potential difference. And remember, work and energy are interchangeable. Yes, the work done to move it from point A to point B, just like the work done in lifting a rock gives you potential energy. If I was to take that and divide it by the mass of the rock, I would get the potential difference. Not the potential energy, but just the potential, okay, the voltage. In this case, if I take the work done divided by how charged that object was, I get the potential. Since work and energy are interchangeable, I can also say that voltage equals energy per charge. Please remember this. I think this is something that's very, very useful. Field strength is force per unit charge, right? So if I want to figure out the force on a charge, I just take the strength of the electric field times the charge of the object. Voltage is very similar, but instead of forces, we're talking about energy. Now this is slightly confusing. Please recognize that this E is different than this E. Okay, this upper E is talking about field strength. This lower E is potential energy. Okay, and so if I want to find out the potential energy that something has, I need to know the potential difference times the charge. All right, so voltage deals with energy, field strength deals with force. Okay. In your data book, now notice that if this is potential energy, and let's say I drop a proton through an electric field through a potential gradient, what's that potential energy going to become? Kinetic energy. And what's the formula for kinetic energy? 1/2 mv squared. So I can also say that potential times charge equals, sorry, my little things are getting in the way here, equals 1/2 mv squared. Okay?
Square root of 2 times the elementary charge times
You bet.
over m.
Sure. And here's the equation. Boom. Okay? Let's get rid of this drawings. All right. So voltage times the charge of the object that's moving through that voltage is equal to the kinetic energy that object will get. This second V is velocity. The first V is voltage in this equation. This is in your data booklet, but they write it slightly differently. Instead of Q, they use the letter lowercase e, which stands for what? The elementary charge. Because generally we're talking about electrons when we do this, so I guess that's why they wrote it that way. So if I take the charge of the electron that's moving through a potential difference, and I multiply it by the voltage, I can calculate how fast that electron will be moving, assuming I know the mass of the electron. Okay? Pretty cool. No. Yeah, so if I know the mass of an electron, I can do that. If you look at your data booklet, I believe this is the first equation in the electricity section, topic 5. Okay, so just be aware of that's what they're talking about there. Something to remember is that potential is a scalar quantity. It does not have direction. It's just tells you something about how much energy is stored in the field at that location. And what do you think we use for the units for electric potential? The unit for electric potential. We've already said the word quite a bit. It's a volt, okay? Named after Alessandro Volta, the great Italian physicist. And 1 volt, this will be helpful, I think, in your understanding of this. 1 volt is equal to 1 joule per coulomb. Okay, remember joule is the unit for energy. Coulomb is the energy of charge, or the unit of charge. So if I say that this location right here in space has a voltage, has a potential of 25 volts, all right, and I pull out this rubber ball out of the drawer, and this rubber ball, I add some charge to it. It now has 1 coulomb of charge. This thing's charged up, 1 coulomb of charge. And I place it right there. How many joules of energy will it have? 25. 25 joules per coulomb. 1 coulomb of charge, 25 joules of energy. Now I take this thing and I give it some more charge. It now has 2 coulombs of charge. How many joules of energy will it have? 50. But this still has a potential of 25 volts. But now this thing has 50 joules of energy. I give it 4 coulombs of charge. 4 coulombs of charge. How much energy? 100 joules of energy. But the potential stays the same. Okay? What if this thing has no charge at all and I place it there? 0 charge. How much potential energy does it now have? 0, because it doesn't have any charge, so it's not going to feel any force, so no potential energy. Boom. Okay? Now remember, we talked about potential being the amount of work to move a charge from point A to point B divided by the charge on that object. But when we talk about potential energy, we always want this universal reference frame, and that universal reference frame happens to be infinity. So if we were doing calculus, we could do some fancy calculus. You don't need to do that, but recognize that we could calculate how much work it takes to move a charged object from infinity to a certain location. And if I divide that by the charge on the object, that tells me the potential at that location. It turns out the work, you don't need to know this equation, but the work to move it would be equal to this. No, to point P, to this point P, okay? And since the potential is work divided by charge, one of these Q's cancels out when I want to know the potential at that location. And there it is. Okay? The potential at a location a certain distance r away from a charged object Q is equal to this equation. I can now calculate the potential created by any charged object. That would be volts. This equation is exactly the same. The only difference is instead of K, they use 1 over 4 pi E naught, which is, and it's in your data booklet. I just want you to be aware of it. Rarely ever does that equation get used, but it's exactly the same. They just substituted for K this other constant E sub 0, or E naught. Equipotential lines. Excellent. What does equi mean? Equal. When we're not talking about horses, it means equal, right? Because other equine is horsey stuff, right? Equestrian. But no, we're talking about equal. Equal potential lines. We can make a map. Remember we drew lines for electric fields? Well, we can also draw lines for potential, okay? And here's an example of one. Here are 2 plates. These solid lines are the field lines. Those are the electric field lines. The dashed lines are lines of equipotential, equal potential. So, yeah, exactly, like the circles on the thing. So notice that the equipotential lines are always perpendicular to the field lines. And we would say that over here in the positive plate, you have a higher potential than over here. So just as an example, this might be 100 volts. This might be 90 volts, 80 volts, and so on and so on and so on. And anywhere along that line, the potential is the same. Okay, that many joules per coulomb. Okay, here's the next one. Ooh, look at that one. Okay, there's a single charged object, positively charged. Notice the field lines are solid. Okay, the field lines are moving away radially, and those dashed lines are lines of equal potential. Notice 2 things. Well, 3 things. They're circular. They're always perpendicular to the field lines, and they get closer together, you know, the closer you are to it. So the potential gradient is steeper here than it is here. So, Omi, this is more, I think, what you were talking about earlier, how the field strength changes on something like that.
It's like a spider web or a well.
Yeah, roll it. Let's look at one more. Look at that. There's one. Okay. Now there's 2 opposite charges. Notice there's field lines going from positive to negative. Those dashed lines are lines of equal potential. So if I know that this is my 100-volt potential line, that anywhere on this line, an object will, the space has 100 volts of potential. And if I put a 1 coulomb object there, it would have 100 joules of potential energy anywhere on that line. Okay? It's kind of like a topographic map. It's kind of neat. Let's talk about some voltages just to give you some ideas of what some common voltages are. Okay? A typical bolt of lightning has a great amount of potential, hundreds of millions of volts. Okay? High voltage power lines, you're talking millions of volts. Television tube, the old style television like I have at home, it has a pretty high voltage in there. We're talking 10,000 volts in there. Kind of a little bit dangerous to take apart your television. I don't know if you ever noticed there's a big warning sign. Do not take it apart because it can kill you. It can kill you, okay? High voltage. Household outlet here in America, those things that you plug things into, 110 volts. Go to Europe, 220 volts.
I saw a kid
Okay.
stick a quarter in the wall.
And what happened? Boom, okay? Notice there are some household outlets here in America that we use that have 220 volts. That would be the one that you plug, like the washing machine is different. It's a big 3-prong thing. Yeah. Yes. Well, it depends on the country, but that is exactly why you have to have a converter. Because if you plug a device into a 220 outlet that's designed to have 110 volts, it will fry it. It'll burn it. Notice that your body creates voltage. Our body works on electrical functions. Nerves, every signal sent by nerves is done electrically. We use chemicals to do that, but you create a little potential difference across your nerve membranes. Okay, so think about that. Ooh, you just had a thought. That was a nerve impulse. That was electricity. Move your hand. Electrical impulses from your brain, through your spine, down your arm. That's electricity. It's happening. Your heart. Okay, let's talk about voltage again for a second. I want you to recognize one thing. Voltage in and of itself is not dangerous. But that's weird because they're like, don't play near the high voltage power lines. Don't get struck by lightning. Okay? Voltage in and of itself is not dangerous. That Van de Graaff generator, this thing where we were shocking each other the other day, 350,000 volts. Super high voltage. But you touch it and don't die. That outlet over there is 110 volts. Stick a knife in it, you'll die. Okay? Difference. There's a difference. So let's go back to our analogy. Voltage is kind of like the height of the cliff. Okay, voltage is kind of like the height of the cliff. So why does a taller cliff not necessarily dangerous? Well, think about this. Imagine you're standing at the bottom of the cliff. Let's look at the relationship between voltage and electric fields, okay? Voltage and electric fields. So a couple of things here. We know that the work done on a charge is equal to Q times V, right? The charge times the potential that we move it through. But work also equals force times distance. Hey, but force is equal to electric field strength times charge. So I can plug this in for F and get this, okay? And therefore, I can set this, since they both equal to work, equal to that. That's what this looks like. That's cool. And I can cancel out the Q's and say, hey, voltage is equal to E times D. And then I can rearrange that and get an equation that looks something like that. Electric field strength, capital E, electric field strength is equal to voltage divided by distance. And where this equation comes in handy is when we're talking about a uniform field. Basically, if I have two charged plates, if I know the potential difference between them, and I know the distance between them, I can find the field strength. Yes, but it looks slightly different in your data booklet, which I'll show you right now. Okay? That's what it looks like in your data booklet. Negative delta Vx over delta x. But that's what they're talking about. Okay? X is displacement or distance or displacement. And generally, this is when we're talking about charged plates. I can find out the voltage or the field strength between them if I know how far apart they are. A final thing I can do with this equation is if I have a graph of voltage versus displacement, what's the slope going to equal? The field strength. So field strength, okay? Because it's change in y over change in x is the slope. So recognize that change in potential over change in distance will give you the field strength for a nice uniform field. The last thing we need to talk about is this thing called the electron volt. The electron volt. You know what an electron is. You now know what a volt is. What the heck is an electron volt? Well, it turns out it is a new unit. It's a unit of energy. What previously have we been using to measure energy? What was our unit of energy before? Not coulombs, that's charge. Joules. Excellent. Joules are the unit of energy for most average things, like apples and people and cars, okay? But when we get down into the world of protons and electrons, the joule is way too much energy to deal with. It's way more than you ever have to deal with. So we need a smaller unit. And they created this unit called an electron volt to do that. And actually, it helps us in some of our mathematical stuff when we get into atomic physics. Yeah, not too crazy. I'll show it to you in a second. The definition of the electron volt is how much energy it takes to move one electron through 1 volt of potential difference, or how much energy an electron would gain if it moved through 1 volt of potential difference. Now remember our definition of voltage. Voltage is energy per charge. So energy is voltage times charge. So if 1 electron volt is a certain amount of energy, and it's the energy that's equal to an electron moving through 1 volt of potential difference, well, really, then the electron volt is just equal to the charge on the electron. That's how many joules of energy it is. So that's exactly what the conversion factor is. 1 electron volt is 1.6 times 10 to the negative 19th joules. I believe you have that conversion factor in your data booklet, but I could be wrong. Okay, this is basically summarizing everything we've done so far. Now, this is a comparison of gravity to electricity, okay? Notice that gravity acts on mass, of which there's only one type, and electricity acts on charge, of which there's positive and negative. There is a force associated with gravity, which is gmm over r squared. There's a force associated with electricity, KQQ over R squared. Very similar equations. The relative strength, you don't need to necessarily memorize this, but notice that electricity is a heck of a lot stronger than gravity. Okay? Much, 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 much stronger. Let's figure out field strength. Gravitational field strength is GM over R squared. Electrical field strength, KQ over R squared. Very similar. Potential, this idea of how much energy is stored in the space. Gravitationally, it's negative GM over R. Electrically, it's KQ over R. Again, very similar equations. The work done in moving an object through a potential is independent of the path taken. I want to explain that again because there's always a question about this. So let's look at, there's our potential energy equations, and then this note at the bottom is just that constant K. The work done is independent of the path taken. If I have a potential here of 0 volts and a potential here of 100 volts, okay, and I move an object from here to here that has 1 coulomb of charge, it just gained 100 joules of energy. You with me? 100 joules of energy. If I move it from here to here to here to here to here and to here, it gained 100 joules of energy. It doesn't matter how you get there. Okay, the work done is the same, and the energy gained is the same. I could also take it here and here and here and here and here and over to there and back, and yes, 100 joules of energy is gained. Okay, so the path is irrelevant. Someone astutely noticed in the other class, then why do we take switchbacks when you climb a mountain? It doesn't change the energy that you've gained or the work that you've done. It makes it easier. It makes it easier to do the work, but the work done is still the same. Here's some practice problems. I just want to at least look at these so that we can start thinking about what problems might look like in the stuff we've been talking about. So potential at point P is 12 volts, and a charge of 3 coulombs is placed there. This is pretty easy. How much potential energy does that charge have? 12 volts, 3 coulombs. What is a volt? What's the unit of volt?
Times 3.
But what is the volt? The unit for a volt?
1 joule over 1 coulomb.
Joule per coulomb.
Yeah, that's
I've got 3 coulombs. I'm going to have 12 joules per coulomb.
So it's 4.
And I've got 3 coulombs.
4.
Oh, and it's the 3 divided by 6.
Because I've got 12 joules of energy for every coulomb of charge.
36.
36. Okay? What would the electric potential energy of an electron be if placed there? How would you figure that out?
Isn't that the same?
Not 36. And would you divide by the charge of an electron? What would you do?
Yeah.
Multiply. Okay? Remember this, that energy equals potential times charge. Because our definition of potential is energy divided by charge. Okay? What would the kinetic energy of a proton be if it was allowed to fall through a potential difference of 110 volts? How would you figure that out?
Oh, it would just be all the voltage going into kinetic.
But would it be the voltage?
Releasing.
Yeah. So you take 110 times what? Charge of a proton, if we're talking about a proton,
Elementary charge.
and which is the same as the charge of an electron. Please remember that. Proton, electron, same charge. Okay, excellent. How fast would this proton be moving? How would you figure that out? Because that energy would become kinetic energy, so we just use 1 half mv squared, and the mass of the electron.